Hello everyone, in this video I'm going to prove this theorem for you by using contradiction method. So this video is not about only proof of this theorem, and also you will have practice by proving theorems by using contradiction method. And also end of the video I will give you extremely important remark, and maybe in your exam they will not ask proof of this theorem, but they may ask that remark to you. So please watch this video. Let's start. How can we prove one theorem by using contradiction method? If you want to prove one theorem by using contradiction method, you should separate your theorem into two parts. All theorems has two parts. First part is assumption. You assume something, something, something. And the second part is the result. In first part, you assume something, 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 and also you will get one result. So consider this theorem. This theorem says that if limit an is a, this is an assumption. Limit bn is b, okay, this is another assumption. Then for all n values, an must be less or equal than b. This is another assumption. Then by using these assumptions, the result will be a must be less or equal than b. Do not forget that a is limit of an and b is limit of bn. How can we prove that how can we prove this theorem by using contradiction method? First of all, we should assume the contrary of the result. The result is a must be less or equal than b, right? Let's say that a is not less or equal than b. A is greater than b. When you assume the contrary, you will get one contradiction. And when you get your contradiction, you prove your theorem. So how can we find our contradiction? The only thing we know about this theorem is limit, 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 limit. So we are going to use the definition of limit. And as all you know, the definition of limit means that for all epsilon values which is greater than 0. But I want to say that we are looking for contradiction. So we don't need to use all epsilon values. We can pick specifically one epsilon. I want to choose epsilon is a minus b over 2. This is greater than 0, right? Because I assume that a is greater than b. So a minus b must be greater than 0. So if a minus b is greater than 0, a minus b over 2 is greater than 0. Then the definition of limit is for an, what is it? There exists n. I will use the same definition for bn, so I want to say not n, n1. What is it? Such that for all n values which is greater than n1, we have what? Absolute value of an minus a is less than epsilon. And do not forget that we pick specifically our epsilon. It is a minus b over 2. If you prove that this is incorrect for at least one epsilon, you prove your theorem, because the definition says that it must be satisfied for all epsilon values. Then let's continue. Let's use the same definition for the limit of bn. There exists n2 such that for all n which is greater than n2, we have what? Absolute value of bn minus b must be less than epsilon. And as we said before, epsilon is a minus b over 2. Now I want to talk about the both inequalities. So I'm going to say that let n is the maximum value of n1 and n2. So I guarantee that then for all n which is greater than n, if I say that for all n which is greater than n, it's already n is greater than n1 and n2, because n is the maximum value of n1 and n2. Then I have this inequality and this inequality at the same time for all n which is greater than capital N, right? So let's write these inequalities. The first inequality says that absolute value of an minus a is less than epsilon. and epsilon is a minus b over 2. And I will use the same inequality in here for bn, of course. Absolute value of bn minus b is less than a minus b over 2. You remember the definition of absolute value, right? If absolute value of an minus a is less than something, it's still less than something, but it must be greater than the negative value of that something, right? So we can use the same definition, the definition of absolute value. Bn minus b must be less than a minus b over 2, but it must be greater than a minus b over 2. This is the definition of absolute value. So now we are trying to find some contradiction. Consider this assumption on this theorem. It says that an is less or equal than bn. We compare an and bn. But in here, we have an minus a and bn minus b. So in this inequality, if I add plus a plus a plus a for all sides, I will have only an, right? I will find the boundaries of an. And also I need only bn here, but I have minus b. If I add plus b plus b plus b for all sides, I will get a minus b over 2 less than an minus a plus a. We get an, and also that one. Similarly, if you add b for all sides, you will get b minus a minus b over 2. Bn minus b plus b, we have only bn. And also b plus a minus b over 2. Now let's write them again. You know that a is 2a over 2. So 2a minus minus b, we have plus b. So we have a plus b over 2 less than an. And also, we don't need to do this, but you can do that, doesn't matter. And also consider here, actually you don't need to do that one as well, but let's do it. This is 2b over 2. So we have only 3b minus a over 2 less than b. And when you sum them, here you have 2b over 2. So when you sum them, 2b minus b, we have b. So plus a, we have a plus b over 2, right? Am I correct? Now, how can we compare an and bn? We have common term. This common term for these inequalities is a plus b over 2. Here a plus b over 2. Let's look at this. A plus b over 2. An is greater than a plus b over 2, right? So I will write it again. This is greater than a plus b over 2. And also bn is less than a plus b over 2. So bn is less than a plus b over 2. Do not consider this term. Just write bn is less than an. So this is a contradiction. This contradicts. Why? Consider here. This contradicts to. Do not forget that was the assumption on theorem. It must be for all n values, an must be less or equal than bn. So this contradicts to an must be less or equal than bn for all values of an, right? So that proves the theorem. When you assume the contrary, you have contradiction. So if your limit an is a, bn is b, and for all values of an, for all values of n, an less or equal than bn, you always have a must be less or equal than b. So this proof is completed. This proof is completed. So this is the proof of this theorem. But what about the remark? The remark is, I will give you one important remark. what if I'm changing this theorem? Let's say that again, limit of an is a, limit bn is b, and also for all values of n, if an is strictly less than bn, then do we have a is less than b? They may ask this remark to you, because in this theorem we prove that a must be less or equal than b, but for when an is less or equal than bn, we have that one. But what if an is exactly less than bn? Do we have that one? No, the answer is no, because if you say that an is 1 over n plus 1 and bn is 1 over n, then you can see that for all values of n, an is always less than bn, right? There is no equality for every n. Always an will be less than bn. But when you consider the limit of an, what is it? It is 0, right? 1 over n plus 1 is 0. So limit of bn when n tends to 0, tends to infinity, 1 over n will be 0 again. It doesn't matter for all values of n, if an is exactly less than bn, your limits can be equal. You can see that counter example. So this one does not satisfy that one. You always have an equality. Even if for all term of your sequence is less than the other sequence, it doesn't matter. Your limit can be equal. So this is an example for that one. Thank you for watching my video. Goodbye.